Hello, everyone. Good afternoon. I am Srihari, and I work at Nilenso. That's also, incidentally, my Twitter handle. So this is a talk that was proposed under the fun category, so I hope it's fun. And it's also a talk where you can lay back, relax. There's not a whole lot of heavy Clojure in it, but it tends to be heavy on the music side. So if that's interesting to you, you will like this. So this talk is mostly about my journey of how I went about making music be generated by machines and how that music can be made more like human music and more melodious. So that said, should we listen to some right away? Yeah? Okay. So here's the code that generates or synthesizes, plays the synthetic music, and this is what it sounds like. Yeah, so that was the machine rendering a piece of transcribed music that I wrote down. So that music is actually a piece of Carnatic music, and I guess I'll get into that in just a bit. But quickly about why I do this. I've learned to sing for like 15, 16 years. I perform rarely, but that's one of my passions. Another one of my passions is computers. So this is a bang intersection of these two things, so I can be creative and productive at the same time. A bunch of the papers that I have to read in order to do what I do are written in the last 5 years, so it feels like I'm bleeding edge research. That feels good. I have a bunch of dreamy ambitions, so I want to be in my room and ask a machine to make 2 hours of music according to my emotion at the time and the time of the day. And so that's sort of the end game for me. And that music needs to be new. So there's that. And in my journey, I've also discovered that there are a bunch of these nice things that can be made into nice applications, and these are the byproducts. I'll talk a little about that in the end. So this talk is going to be in 4 phases. So we have first melody. So we'll try to understand melody and try to dig in, find abstractions that we can use to model and then synthesize and generate music. The second part is going to be modeling. So we'll take those abstractions and write them out in Clojure and see what best we can do there. And then synthesis is about taking some transcribed music or notation and rendering it in a way that can be close to a human. And generation is about the machine creating music by itself. When I started out, I thought these would be, wait. There. Yeah, when I first started, I thought this would be a linear process, but it's more of a cycle. So as we synthesize and generate music, we understand things that we need to feed back into our basic understanding of melody and then model it again, and this is a cycle. So since this audience is into definitions at the beginning of talks, so here's one for you. So what's interesting about this is that the definition says something about a melody being musically satisfying. So there's a human subjectiveness to this, right? So it needs to be vetted by a human. And we'll have to find out how to model something like that, right? And then another part of it that's curious is a notion of single notes. And there is an implicit notion of notes being the fundamental unit of abstraction in music. And I question that. And I question that in the context of Carnatic music, I guess. This would be a good time to give you all a nice 5-minute crash course on Carnatic music, and I'm going to give you a piece of music so you can intuitively understand it instead of me explaining it. So here's some Carnatic music for you. right? So you'll notice that it sounds unlike other Western music. It's played on a violin and was an extempore piece in the Raga Kalyani. I'll get into that soon, but now I'll give you a video of it so that you can look at it and understand it even better. Right, so you notice that there is a main artist, and for the entire context of my presentation, that's the guy I'm going to care about, and that's the music I'm going to be looking to synthesize and generate. There's an accompanying violinist at all points in time. There is a single main percussionist, and there is a drone, which is the tanpura, consistently in the background. And I guess this should give you a good idea of what the concert picture is like. But on a broader sense, though, Carnatic music is South Indian classical music. So the earliest treatise on this was written in 500 BC, and it's called the Bharata's Natya Shastra. So it's like quite old, and even there are like details of ragas and swaras and gamakas, right? So these abstractions have existed for quite a while and have evolved. The other thing about Carnatic music, it has these abstractions called ragas and gamakams. And these are things that we can use, right? So we have these additional constraints now that will help us create more beautiful music. So that's another reason why this is interesting in that context. It's also a vocal tradition in which I learned from my teacher. My teacher sings, I repeat after him. I mostly don't write down anything. Historically, nobody has written down a lot of things. So there's a lot of content, a lot of information that's just intuitive. And a lot of this talk is also going to be uncovering those intuitions. It's also rich in compositions. So in a typical concert, you'll have a bunch of songs that everyone sort of knows already, and there will be re-renditions of them. And there are pockets in the concert for improvisation, and this is called manodharma. So a lot of the concert music and the expressions of artists come out in these areas. Quickly, though, because I might refer to these later during the talk, that's a veena, which is a fretted stringed instrument. It's almost exclusively used for Carnatic music. That's the tanpura, or the drone that you saw earlier, and the mridangam is the main percussion instrument. So with that, we have a bunch of musical abstractions in Carnatic music now that we can model over things that we already understand. First of which is Shruti. So this is the tonic note. Like as a concert artist, I would pick a single pitch, and every other note that I render would be relative to this. A female artist, for example, would pick a higher pitch, and that pitch or that tonic note can be any one of the standard frequencies, and that's a map that represents that. There's also a concept of laya, which embodies the rhythm concepts. I'm just leaving it here for completeness. It's not important in this talk. So just so that you have a comparative understanding of what these notes are in Carnatic music, here's a single octave on a piano, and these are the notes in Carnatic music. These are called swarams, right? So you have sarigama padani. So that's how you pronounce them, but when you write them, you just write SRG, MPDN, and you have a bunch of variations of them, right? So you have 3 ris, 3 gas, 3 dhas, 3 nis, and 2 mas. This is in Carnatic music, right? Now that you understand these, we then write them in Clojure, so that's pretty much it. So you have a single neat map of all the variations of the swarams written down, and each of them map to an atomic relative MIDI number, right? So you have 0 to 11, those are your semitones. And you have simple swarams, those are the things that we utter, and those are interpreted in the concept, within the context of a raga. There's thais, which are your octaves. So I've modeled 2 octaves up and 2 octaves down as 5 octaves. Now we can go on to understand the abstraction of a raga. And here again, I'm going to rely on your intuitive sense of understanding what this means. Right? So that was a raga called Kapi. And ragas are a flavor, right? So each raga can be thought of as a flavor or an emotion, right? So I can think of happy ragas or sad ragas or melancholic ragas or angry or like pleading ragas. So these are the things that are embodied in a raga, but more theoretically, a raga is composed of swarams, right? And there is also a notion of an ascending rule and a descending rule. These are called the arohanam and avarohanam. And these things need not be symmetric, right? So the ascend rule and the descent rule need not be the same. And they need not even be linear, so you can have jumps. So the ascent might have 0, 3, 1, 2, and that's fine, right? So that defines a raga. They're classified, and I'm not going to go into all that, but let me just tell you there are a lot of them. So this is a single EDN file that has 17,000 lines of ragas. Like there are like 5,000 ragas in all of this, and this is just a bunch of scraped content. But now that we have built these musical abstractions, a layer on top of whatever we already know, let's use something like Overtone and like see what we can get out from what we've built so far. Right, so that's me in the REPL. So I can look up the Eden map, right? So that's simple. That has a name. There's the Arohanam, Avarohanam are lists. I can also fuzzy search a raga, and this is important because it's an Indic language fuzzy search. So G-O-U-L-A and G-A-U-L-A need to pick up the same thing, right? I can talk about that importance more in a bit, but you can play a scale. Right, so that just played the ascent and the descent of the raga Bilahari. And here's another raga. Right, so this one's symmetric, the previous one wasn't. And then you can play swaras and give them durations and play them at a particular speed. Right, and so you'll notice that these are actual swaras like Ritu, Gatri, and I've given them names and the durations. You can increase the speed, of course, right? And then you can interpret these notes within the context of a raga. So this is where it sort of gets interesting. Right, so this is within the context of Kalyani or Major Kalyani. Now, if I change the raga, right, right? So this is actually a mind-bendingly difficult exercise for me to do as an artist. Like I need to get into that raga, understand it, and then render these notes. A machine can just do it. So that is a piece of prescriptive notation, right? Written as a string with commas representing. So this is what I would write down in my class with my teacher, and I can now render that. Right? So we've gotten this far. And the things I use are fairly straightforward. Overtone, Leipzig for the melodies and durations and such. And I'm using Postgres's inbuilt fuzzy extension to build this. So the fuzzy search, right, needs to use a combination of SoundX and Levenstein because just Levenstein isn't enough. SoundX is an algorithm that tells you how close two words sound like each other, so I need both of them. So far, though, we've played a scale of a raga, we have fuzzy found a raga, we've played a phrase, we've gotten a phrase within the context of a raga, and we have played some prescriptive notation, but anyone with any experience listening to Carnatic music will tell you that that doesn't sound anything like it, right? Like, if it doesn't even sound anything close to what you heard before. So this brings us to synthesis, right? This is the process of making your machine sound more closer to how you would sing. But we have little idea by just listening, so let's see them instead. So on top is a melograph of me singing something, singing some prescriptive notation, and the bottom is the machine rendering the same prescriptive notation. Let's listen to both of them. And that's the machine now. Right? So this is pretty obvious, right? You have continuity in me and no continuity in the machine. Yeah, and there's basically no curves or whatever. But if I change the instrument to a sine wave instead of a saw wave, it sounds softer, and actually, if you consider a longer phrase, it actually sounds closer. Let's listen to this. Okay, now watch the same phrase by the machine. Right. So if you actually look at the graphs, they actually sound close, look close. So there's a Batman ear type shape on the top. If you can see the same thing at the bottom, you'll see that, oh, they are the same thing. But you'll notice that the machine is still very squarey. There aren't transitions from notes to the other note like in my rendition. But digging into that a little bit, let's try to understand what is the difference. So this is just me drawing the melograph by hand so that I can illustrate something. So this is a piece of prescriptive notation. The first thing is pa, like the fifth note, played for two durations, but it spans 3 notes. So it spans 4, 2, and 7 at the same time, and that is just uttered as a single note, right? So that's clearly information that we're losing. And I guess that brings us to another abstraction for us to understand. So these are called gamakams. In reality, I do not understand these gamakams as a learner. My teacher just sings, I repeat, right? So this is a concept that seems to exist in theory, in textbooks, in various literature pieces, but isn't understood in day-to-day music. So let's understand Spuritam. Let's listen to some, actually. So you see that dip in between the inverted triangle? So that's actually the Spuritam. The Jaru is a gradual ascent. Let's listen to that. Right? So that gradual ascent is also called a gamaka. The Orikai actually is an interesting gamaka because it spans across multiple notes, like 4 or 5 of them. Kampitam is just oscillation between 2 notes, and there are a bunch of them listed here. So this is a book that actually came out 300 years ago. It was written by Raga Dictionary. It's called the Sangita Sampradaya Pradarshini. He actually has notation, and he uses that in notating his own work, but this is not done on a day-to-day basis. So he has these gamakams written down and ways to combine them, and multiple gamakams written down prefixed before each note. But as far as writing these in software, modeling them in software is concerned, I'm not the first to do them. So there's Gayaka, which exists. It's built in, to run only in Windows. There's a database of phrases which he's manually made. So like basically write down every possible trigram of swarams and then map the probability of the gamakam existing and all the possibilities of the gamakam and their probabilities. So it's like around 300, 400 probabilities per raga, and that's a lot of work. But the way he models them is interesting because he has parentheses and angular brackets. They represent speed and increase and decrease of pitch, and these are the only 2 things he uses to control gamakams. That was interesting to me. And I tried modeling the SSP kind of gamakams myself. So here's more code for you. So this is an overtone instrument, right? And if you notice inside the LED block, there's an env gem on the gamakam env, right? And that's applied on the sine oscillator, which means that it's an envelope over frequency. Now, that's not very common in synthetic music. People usually apply envelopes on amplitude. So I need to shape the frequency curve, and so that's what I'm using. So you'll see in Spuritam instrument and Jaru instrument. So Spuritam instrument has FF, LF, FF, right? So that's the shape of the Spuritam curve. And then there's the Jaru instrument, which is like previous frequency to this frequency, except take a lot of time to do that, right? So and do so in a Welsh curve. So that represents the shape of this gamakam, and I can infuse them in between, and this is how that sounds. This is the same phrase as before, right? Right? And you can see at the right top, there's how I've prefixed the notes with my own symbols to represent gamakams. And you'll see that these dips now exist, and the kampitam also exists. So this is actually much closer, but I chanced upon this other work by Srikumar. It's also in the recent past, in 2013, and he has this thesis on this, and I read the whole thing. So he represents these movements between pitches as arrays of 4. So instead of ADSR, it's PASR, which is pitch attack sustain release. And you'll see that the first one, PA, for example, has a list of 3 arrays, 3 vectors, and you'll see they have 4, 2, and 7 as the first note. So this is exactly the same thing that I drew out by hand earlier for you. And the ASR notation is that. So it's like, take 2 durations to go from 4 to 2, and then go to 7 in 2 other durations, and stay at 7 for 4 other durations. Right? So that is what that represents. And this is actually fairly easy to implement, so I did. And let's listen to that. So that's the exact same phrase of the prescriptive notation earlier. Let's listen to the machine. Right? So that's the 4 to 7 transition that you see, and it's very neat, and it's quite close to me, right? And this is so good, I think you guys should listen to some more. So here's some prescriptive notation and the machine rendering it. Yeah. So at this point, I was happy. I was like, okay, now I have the flavor of Carnatic music in my machine synthesized music. So I was happy, but I knew that I have to manually transcribe this music, any piece of music, into this notation to do this, and that was painful. And my other aspiration, of course, was generation, right? Like having the machine create the music. That's where all the good stuff is. So the first thing that I tried is the regular aimless wandering musical, algorithmic music generation technique, which is basically just pick any random swaram. But I already have the abstraction of a raga, right? Like I can pick any random swaram of a raga, and that's what I did. So I can get rand nth of any swarams that you pass to it within a raga. And I have a simple algorithm to generate durations such that after a certain number of bars, you hit a multiple of 16, and that's why you stop. So let's listen to that a bit. Right? I really wish I had that slider thing. That would have been super useful. But you can follow along the graphs as you listen to the music. So this is actually okay music. It sounds better in some ragas than this one. But you can see that there's a lot of up and downs. There's a lot of jumps. And it doesn't, although it sounds in tune and everything, it doesn't sound very musical. And at this point, I basically hit a wall. And I'm like, okay, this doesn't sound musical. What do I do? How do I make this better? So I'm basically searching for abstractions that I can use and a better understanding of melody that I can use, and I don't have it. But also part of the reason why I don't have it is because I don't have the data. And Carnatic music is actually not in a place where Western music was even 10 years ago. So there isn't a Grooveshark or Spotify equivalent. All the music is in everyone's personal collections, and there isn't a common place where everything is put together. So I created one such thing, right? So I wanted to create a music Brainz equivalent for Carnatic music, and this was basically my work for the next 6 months. Basically scrape every website that I can and get the music data that I can get. So all these scrapers are in the same repository. Now I can scrape all these 3 websites, and Sangeetapriya actually has the most musical content. I can scrape all of this in all of 3 minutes time from scratch. Anyway, so I then built a website for myself and my friends to actually look up this music. Actually, after all these years, we have a Raga Dictionary, something that I thought would have existed until now already. Anyway, so now I'm in a position where I can say, search in my database, look for all ragams, all renditions in a raga, say Bhairavi, get me 50 of them and download them for me. Right, so now I have data. Then I need to study it, right? And this study of data needs to be in signal processing, and I'm not good at that. So I use tools. So Prat is actually something I discovered from Sri Kumar's paper. And that Prat is actually made for speech synthesis and speech recognition, but it seems to work pretty well for vocal music. Sonic Visualize is sort of good too, but Prat is what I use because it has a nice autocorrelation algorithm that picks out the frequency data that I need, and it has a command line interface. So then, it was just that I had to use Incantor, read the frequencies of the file, and put them in a graph. And so, yeah, it's an XY plot, and then I have melographs, right? So these are the graphs that represent an entire rendition, right? An entire song or an entire composition. So I started these for a very long time, but I can tell you a few of my observations right away. So first thing is that you'll see a line through it, a constant thing, mostly, and that's in, like, my hypothesis was that that is the tonic note. And similarly, on this one, you'll see that there's a line. And there's another line on top, which is usually the next octave in the same tonic note. There's sometimes a line on the third and the fifth as well. That tends to be prominent. And you'll notice some patterns in ascension and descension, depending on the quality of the data. But another way of looking at this data is to make a histogram of it, right? So you take the frequencies, throw away the data of sequencing of notes for the moment, and look at just the histogram, which is this. And at this point, I was like, aha, I see my raga here. So going with the hypothesis that the biggest note there is the tonic note, I have my notes. So if that is sa, I have rigama, pa. So pa is the in-between frequency, the fifth, and then dhani sa, which is the other peak. And I notice a bunch of other things. So first thing is that in the octave lower from the primary tonic note, you'll see there is only one peak, which is the lower fifth. And then 2, 3 notes on the higher octave there's only 2, 3 notes on the higher octaves, and the peaks are actually lopsided. So you'll notice that the tonic note has a small lopsided peak on the left. The fifth also has a lopsided peak on the fourth, and this is interesting because I know that this raga has the fourth very close to the fifth. And now I have that information, right, which is great. And I started this a whole bunch as well. Let me do a quick walkthrough of these for you. So each row is a different raga. Kalyani is what we looked at. The violin rendition, though, you'll see that it has a peak even close to the tonic note, and that's because it's on a violin, and for some reason he chose to emphasize that note more. Look at the mandolin one, though. That's kind of interesting because mandolin is a fretted instrument that's used for playing Carnatic music, and it's not orthodox to do so. And you'll see those peaks as a very thin peaks, and the reason, and that's sort of how you would see a pitch histogram for a guitar, even, for example. A Revati has a different lopsidedness. It has a lopsidedness on the tonic note on the right side. That's because that represents that raga. And the right bottom is actually an example of noisy data, and that's the sort of stuff I have to deal with because the data isn't clean yet. But that represents the raga, but that histogram is useless. Anyway, but now that we have studied the data, we need to get the data into the abstractions that we have already built, right? So the abstractions that we have built are swarams and ragas. Now, how do we use this information? So one way to do that is take the pitch histogram, approximate every single frequency to the nearest MIDI note. So from a continuous list of frequencies, now you have a discrete list of frequencies. And this is accomplished using Overtone core, Hertz to MIDI. That's convenient. And then I fold the octaves together, and I have a single octave with the frequency of every note, which is what you have here. Now this is actually good, but it's not useful to me yet because I don't have swarams. And the reason why I don't have swarams yet is because I need to identify the tonic note. And all the other swarams are related to that. But tonic note identification is still in the signal processing research phase, right? So these are papers in the recent past where people have actually explored pitch histograms, which told me, yes, I'm on the right route. And they explored different ways, like isolate the drone and find the tonic note there or whatever. But from my experience, just pick the highest frequency, and that mostly seems to work. So how I do that is this single function that does it for me. So basically, create frequencies, normalize octaves, and sort by values and pick the first one. And now, if I have identified the tonic note, if you remember the earlier map that I had built of the simple swarams to the MIDI histogram, sorry, the MIDI relative notes, I just need to do a reverse lookup on that, and I'm gold. So I have this, right? So I have a histogram of swarams in a raga, right? So this is abstraction that I have already built, and this is information that I can use, right? So I can see that first, fifth, and the second tonic note, next octave, are prominent, and all the other swarams in the raga are prominent. Here's histograms of a few other ragas. This is Mohana, Kalyani. So actually, Mohana has only 5 notes, and you'll notice that between the 2 tonic notes, there are only 4. So these histograms represent ragas correctly. And now what I can do is use this probability information and generate music with that. And that's what I did, right? So it's as simple as that. I just bucket them off into probabilities and then pull the next swaram based on those. Here's what that sounds like. So this actually doesn't sound very different from the random one, or it might not sound that different to you, but it is. So to put things in context, what I did was I played it along with a ukulele. And so here's what that sounds like. Right? That sounds nice. Steve said it sounds like an 80s game or something. So that was relatable. And then my friend said, I asked my friend, okay, what raga do you think it is in? And she said, Mohana, maybe? And then she was right? So there lies the concept of subjective human interpretation of melody. And this is validation, vetted by humans. So the melographs, though, you can compare and contrast them. You might not see a lot at the first glance, but then if you look at it a little deeper, you'll notice that there are lesser ups and downs. The random thing tends to have a lot more of them. So let's quickly review the insights that we have had until now. So first thing, the tonic note is prominent, right? And then the first and the fifth have sharper peaks. So this is something I intuitively understood as a musician. I was like, I just don't have a lot of gamakams at sa and pa, but now I can actually see that and model it, so that's great. It was like a rediscovery moment. Other notes are blunt, other swarams are blunt peaks, and probabilities of all swarams in a raga are not the same. That's probably an important discovery. And probabilities across octaves of the same swarams, like the same swaram in different octaves actually has different probabilities. What's the next step, though? The next step to me was model the continuity, right? Like what comes after the other one. Excuse me. This was quite easy to build. So instead of building a histogram of the linear frequencies, all I need to do was line them up 2 at a time and get frequencies of that. And then I can use this information now. We move to a whole new level now, though. There's first the prominence of adjacency. So notes that are close to each other have higher probabilities now. So we should have a lot lesser jumps. So that's great. The second part of it is that it now adheres to the grammar of a raga correctly, right? So you have arohanam and avrohanam. I mentioned that these need not be symmetric or even linear. So if you have 4-8 instead of 4-5, now you will see in these probabilities that the 4-8 probability is a lot higher than the 4-5 probability, which encodes the rule of a raga. So that's great. And now all I need to do is build a lazy sequence from these probabilities. So I have a stream of music notes that I can now play. So let's listen to some 2-swaram weighted music. right? So that sounds spooky, I know. That's what everyone in the office also said. But it sounds like music, really. And I was like convinced that, hey, it's Carnatic music, and I can actually see Mohanam things in it, and I can see gamakams, and there are ups and downs that are great, and it sounds more continuous and like my voice. So that's great. So the insights, really quick, are that swarams close to each other sound a lot better. The rules of Arohanam, Avrohanam are encoded. There are gamakams, and this is sort of the in-between stage where it's not really good music yet, but it's not even as ignorant as the single probability swarm, so it kind of sounds a little worse than the ukulele example. Yeah. And the next step for me was to look up Markov chains and try to do something more generic and have more swarams in your memory. And really quickly, so this is what Wikipedia's page says about the first order matrix in a Markov chain. So you have one note and the probability of the next note, and you can find, you can continue that line down to the second order matrix. That's the second order matrix, if only it stopped there. Yeah, so that's the second order matrix, and that's like the 3 swarm probabilities. I can just make that generic. So somebody actually already did this and made a generic Markov chain generator. So collation basically builds the probability matrix and renders them. And I have tried this a whole bunch, and it was disappointing, right? So there's 3, 4, 5, 6, 7, 8, 9, 10, and that's the number of swarams I'm holding in memory before I render the next swaram. And it's actually not that great. Like, I imagined that, okay, I got so much so far with 1 and so far with 2, I imagined that it would be exponentially better, but it's not, actually. The graphs actually seem to be better, they're more granular, there's some movement, but it doesn't sound good at all. So I guess one conclusion was that maybe music cannot be a Markov chain. And another defeat at that was that, LSTMs will not work too, right? And I was really looking forward to more doing deep learning on this, and then this really dampened all my heightened emotions on that. Yeah. So what I did get, though, are a couple of very good byproducts. First thing is automatic transcription. So this has not been done for Carnatic music ever before. So I can take a piece of music and infer the tonic note and everything from that and give you actual notation. This is something I can give to my friend and say, hey, you can learn this piece of music, here's the notation, and they would be able to do that. It's not quite as good as it needs to be, but I'm sure I can get there soon. Another really good byproduct, I think, was Raga Identification. This is a bit of a fad amongst Carnatic musicians. In the beginning of a concert, in the beginning of a song, within the 10 first seconds, everyone's like, oh, what's the raga? And then the people who understand it get it fast. And there are also Raga identification competitions. And now my machine can participate in it. So here's how I did it. This is what I learned from e-commerce days. Basically, just do a goodness of fit tests. Take your histogram, compare it with an incoming histogram, and you'll be able to tell how close they are. Right? So for example, here's in the middle is Mohanam against Mohanam. So you'll see that their chi-square scores are super less. Within 10-ish. Kalyani and Mohanam are close to 10, 20s, and Revati and Mohanam are quite far away, and that's actually the truth. Also, Mohanam is actually a child of Kalyani and is closer, and here's a visual representation of the same thing. So you have Revati versus Revati, and they look similar, and Mohana and Revati look dissimilar. What next, though? Where from here? So first thing is, I want to be able to take all the insights that I have gained and push them back into the generation and use them as algorithms. I'm trying that, I'm getting there. Second thing is, I want to use all the synthesis models, so the SSP kind of gamakams and the passer kind of gamakams, use them in the generative music itself. And then I want to experiment with rhythm. Rhythm has a bunch of problems in the signal processing side still. First thing is, rhythms is not even consistent, and then some places don't have rhythm, and then you need to pull out the rhythm component from the music, so that's difficult. Another thing that would take us very far would be synthesizing human voice. Just a minute, I'm almost done. And another thing I do want to try still is deep learning. And here's a philosophical question that keeps bothering me all the time. Right? When I listen to music, I'm like, okay, this is what the emotion of an artist and the expression of an artist was at that point in time. But if the machine is doing the same thing, is that still music? Would you still respect it in the same way? For the moment, though, I will leave you with a piece of human music, which seems to be better than machines. And that's all I have. Thank you.